Good afternoon, everyone. Good to see you all. Welcome to Intro to Abstract Math. Hope everybody is hanging in there. Got some sleep last night. Yeah, in retrospect, I was expecting this. I'm glad we don't have an exam today. I think things would have been distracted. So good. Plus, we need some time to wrap up this material anyway. So I want to finish up the last worksheet that we were working on last time with equivalence, classes, and partitions. Go through some examples that may help you if you still have some questions on the homework, and then just talk about the exam. Got an exam on Monday. Before we get started, I just want to say there is like a math advising event going on tonight from 5 to 6 that I'll be running. So the information about that is in the announcement. So that's great if you can make it. I'll record it and post it on the math website as well if you can't make it. And also, I want to just show you that up in Canvas, there is a section over here that I added, exam 2 info. So here, we'll go through this sheet later, but you can find that sheet here. And I just want to point out that here's where you can find some additional practice problems from the textbook if you want to prepare. So the exam is on mainly on chapters 10 and 11. But still, like direct proof, contrapositive, contradiction, those are still things you should be familiar with. So exam aside, any questions about anything else before we get started? Okay, so we were kind of almost through. It's always bad to end things like halfway through a proof, but we left things with a cliffhanger. So I'm glad that you came back and tuned in for the conclusion of this proof. So we were working on Theorem 4, which was making this connection between, we talked about what equivalence classes are, we talked about what a partition is, and then it turns out that they're basically equivalent. So given an equivalence relation, we can get a partition. Given a partition, that defines an equivalence relation. So the first part of that sentence that I just said is, given an equivalence relation, the equivalence classes form a partition of the set. So just some reminders, an equivalence class of A, we would say, is the set of all elements in the set that are related to A. So what we'd like to show is that these classes form a partition. And then remember, for a partition, there are 3 different properties that we want to check. The first is that each of the parts is non-empty. So we talked about that last time. That comes from the symmetry requirement of an equivalence relation. Secondly, you want to show that any 2 parts are disjoint from each other. So if I have 2 different parts, A and B, their equivalence classes should not have any elements in common. And so this we proved by contrapositive. No, I'm sorry. We did this by contradiction last time. And that's where we ended the discussion. But over here, we needed the transitive property and the symmetric property. This is wrong. Right, that's using the reflexive property up here. I think I had symmetric. So you can see in this proof, we actually did need all three properties, reflexive, transitive, and symmetric, of the equivalence relation and nothing more. And so that's why these are three properties that are nice to require about a relation, because it gives us a partition of the set. And so we still have one piece left. We didn't prove this last condition that we need for a partition, which is every element in the set must occur in one of the classes. So in other words, another way of saying that is the union of all classes should give us back the original set. So very informally, a partition means that we're going to divide the set up into subsets, and all of those subsets and each element of the original set should appear in exactly one of those subsets and not more. So any questions about this, since this is where we kind of ended things last time? Okay, so then in order to show that the union of all classes equals the set of S, this is like a set equality. So what I'd like to show, just to put a little note down here, that when I take the union of all of these elements, we get back S, and that would give us, so this over here is representing the union of all classes. Okay, so we want to show equalities. That means we want to show like subset inclusion both ways. So first I can say, let's take consider an element A, which is in the equivalence class A. And we know that this is true so we can claim that A is in its own equivalence class because this relation is reflexive. So it's going to be related to itself and thus in its own equivalence class. So I should also just note, I don't know if I said this already, I guess we did earlier, that A is an element from its set. And so that tells me that any element in the set S is going to appear in some equivalence class. Therefore, we're going to get, when I take all of these equivalence classes together, we are going to get back the entire set S. So let me kind of just explain that more carefully. So since every element of S appears in its own equivalence class, maybe I should say and this again comes from the reflexive property. And that proves the fact that every element of the set S has to appear in one of the equivalence classes. And again, this also used the reflexive property. Any questions? And so I'll just say, like, if you look at this proof, you know, this includes a whole bunch of stuff. So inside of here, we have what is the definition of a partition? What is the definition of an equivalence class? What does it mean to be reflexive, transitive, symmetric? We've got set equality. We've got a proof by contradiction. We have a direct proof in here. So you can see how all of these ideas are, it's not like any one question just depends on one concept, but we also want to make sure we're connecting all of these concepts together. Okay, so if there aren't questions, and again, just feel free to interrupt if you do have a question, then I'm not going to go through this proof together. I'd rather spend the time going through some examples. But I just want to say that the previous theorem that we just proved says that equivalence classes of an equivalence relation gives us a partition of the set. And this theorem is going in the opposite direction. It's saying given a partition, we can define an equivalence relation. So equivalence classes and partitions in some sense are not distinct from each other. They're just kind of the same thing. And the way that we would define an equivalence class from a partition is we say that two elements are going to be related to each other if they appear in the same part. And so that's how you define the relation from a partition. But I think the big takeaway that you want to have here is, you know, why are equivalence relations desirable? And it's because they partition the set into a bunch of equivalence classes. And that's a nice property, to have a nice partition. Okay, so question 2 has several parts here, and this is probably familiar to some of the problems on the homework. So I've been talking with some people, and seems like, you know, the properties of relations, proving something is an equivalence relation seems okay, but trying to describe what their classes are, there were some questions about that. And that made sense since we hadn't gotten to this example yet. So for example, if we consider this now familiar relation that we've considered before, the parity relation on Z, by saying, okay, two integers X and Y are going to be related if they have the same parity. So what we'd like to do here is describe the equivalence classes, like how many elements are in each equivalence class, how many parts are there, etc. So by this relation, how many equivalence classes would we get? The hint is, if you've got a camera on, you can indicate that with fingers. So it's less than 10. All right, thanks, John. Yeah, so we're gonna have 2 equivalence classes there. Thank you, everybody. So what would be an example of one of those equivalence classes?
If X is even?
Yeah, so we can take the set of even numbers. So when we write these equivalence classes out, then right, so I could write it out as a set, or I could call it the set of even numbers. Equivalence classes are sets. So one way to describe it in words would be we get the even numbers. If I want to describe it as an equivalence class, then I can pick any element in this set and pick it as the representative for my equivalence class. Who's got a favorite number that's even? What do you think, Victoria? Picking 2. Okay. So we could pick 2 over here. It's no different than if you were to pick 22 or anything else. So there's nothing special about the representative that you pick. You just need to pick one element that's in that set. So this would be one way to describe that equivalence class. You can just call it the set of all even numbers. And then we have a second one, which we can pick any element that you want for that one. And this would be the set of odd numbers. Forgot one. Any questions about that?
Do we assume 0 is even then?
0 is even, yes, because we can divide it by 2 and get, we can write 0 as 2 times an integer. It's 2 times 0, yeah. Okay, any other questions? So next up is this equivalence relation that we can get doing modular arithmetic, saying mod n. And so if we're taking a look at the resulting equivalence classes from this relation, how many of them would we get? So like if we were doing mod 3, what would the equivalence classes be? So we're gonna have 3 of them. Thank you, Victoria. That's right. And so they're gonna be, now it's almost like one step further than part A. Part A, there's no difference between how we did this and saying this is the same as looking at the equivalence class mod 2, right? Even numbers would be in the representative 0, odd numbers would be in 1. So if we do mod 3, this is going to divide the set into things that are divisible by 3, things that have a remainder of 1 when I divide by 3, and things that have a remainder of 2 when I divide by 3. So typically we would write that as 0, 1, and 2. So usually we pick like the, when especially we're doing mod, we pick like the smallest representative of the group. Right, so that would be all of the things that are divisible by 3. This would be all of the things that have a remainder of 1 when we divide by 3, and so on. And now we're only considering natural numbers. So these would be things, positive integers.
What is that third set again?
This one here,
Yes.
this is all of the natural numbers that have a remainder of 2 when you divide it by 3. So if we're looking more generally at mod n, then how many equivalence classes would we have? Might run out of fingers here. Depends. Sorry?
N?
Yeah, thank you. Yeah, so in general, you would have n. So we can you can think about them like this, okay? And if you don't want to pick 0 as one of them. And so here, this would be the set of all things right, that are one more than a multiple of n, and so on. Any questions? So this is the type of description of equivalence classes that are needed. So just write out their set. So write out the elements that are in that set. And if there's a more friendly way of doing it, like just saying even and odd, then that's great too, if you can describe it more simply.
Why didn't we have to start with 0 again? Sorry.
Yeah, I realized that I made a mistake over here, and that 0 is actually not a natural number. Natural numbers are 1, 2, 3, 4, 5, and 6. So I should have done that and not used 0 in that sense.
Got it. Thanks.
Yep. Okay. Anything else? Okay, so then part C is the total relation. And so the total relation in general is the set crossed itself. So the total relation means every element in the set is related to every element in the set. And you can replace Z with whatever set you're describing the total relation on. So with a total relation, how many equivalence classes would we get? Again, you can do this on fingers. Yeah, that's right. We're just going to get one equivalence class here. Since I pick X, X is related to every other element in the set, every other integer in the set. So this would tell me for any total relation, we have one equivalence class. Okay, I'm going to pick my favorite integer, which apparently is 17. That was the first thing that came to my head. So, right, we just have one equivalence class here. And what's another way that we could describe the equivalence class? should be a very nice looking set.
Is it the set of all X and Y such that relate to Z?
So these equivalence classes are going to form a partition of the set, in this case, Z. So they're going to be, in general, subsets of the set that you start with. So what I should be thinking about is this gives me possibly some subset of integers, but the elements in this equivalence class would be the set, generally speaking, of all X in the integers such that X is related to 17. And so what values X would be related to 17?
Would it just be 1 and 17?
So 1 is related to 17. What's another element that's related to 17?
I think, isn't 17 also related to it?
So remember, we're dealing with a total relation here.
Oh, so I guess every whole number multiple of 17?
So the total relation is, here's an element, 17. Every other element in the set, in this case, integers, is related to 17. So 1 and 17, multiples of 17 are in there, but we're not doing modular arithmetic here. What else is related to 17 in this case?
All integers from negative infinity to infinity.
Yep, that would be everything. Since here, we only have one equivalence class. So if we only have one equivalence class and it's giving us a partition, it better contain everything, right? Which it does. So when you have a total relation, it's a really boring relation. You only get one equivalence class and you get a really boring partition of the set. Just here's one set. So here we could describe the equivalence class as just saying it's everything in the set. Okay, are there questions about this? Maybe, who knows? Maybe I'll give you guys a chance to think about D and E. In some breakout rooms, and then we'll come back together, wrap these up, and then spend the rest of the time getting ready for the exam. So let's work on D. We can start with D, and if you wrap that one up, then you can move on and try and think about E. Let's see. Okay, breakout rooms are now open, and Nat and I will be rotating through, checking out on you. Right, welcome back, everyone. As far as the equality relation goes on D, any questions? I don't get a chance to talk with Nat's room, so I can know what happened in the other two rooms. Were there any questions that came up with Nat's group?
No, we were pretty good on D. It took us a bit to figure out how we were supposed to write out E, but I think we got it.
Okay. Yeah, so in D, then the groups that I spoke with were okay on this one after talking about it. So some observations here are that since each element is related to
Are you
only
writing on your
one,
tablet?
Sorry?
Are you writing on your tablet or anything? Because we can't see anything.
That's fine. You're not allowed to see it. We can do it the old way. I can go like this. Does that help? Yes, thank you for that. Let me share that with you. that's what I drew. Very important what you missed so far. Okay, so some observations that came up were, since each element is only related to itself, each class has one element itself. And so since we have an infinite number of real numbers, we're going to get an infinite number of equivalence classes. So here's a term, I don't think we've used this before. A singleton is a set that contains only one element. So one way to say this is, okay, we have an infinite number of equivalence classes. Each class has only one element. So that was part of what this question asked. How big are the equivalence classes? These have just one element. How many parts are there in the partition formed by it? We have an infinite number of parts, an infinite number of equivalence classes. And so if I want to write out what those classes look like, then each class would just look like that. And we have one of those for every x in R. Okay, so in E, we're going to think about some equivalence class that we can define on the real numbers. And so we've got not just whole numbers, not just integers here. And we're going to define two numbers to be related if and only if, when we round them, they have the same, they round up or possibly down to the same integer. So for example, we could say 2.2, that's related to 1.8, since when we round both of those, we get 2. And by that same token, 2.2, for example, is not related to 2.5. Okay, so someone want to share what came up then when you were talking about these? So I guess like the first question is, how many equivalence classes do we get?
We have an equivalent number of equivalence classes basically equal to the number of integers.
Yeah, so we're going to get an infinite number of equivalence classes. And for each integer, we get an equivalence class. So let's take the equivalence class 1. What numbers would be in that equivalence class? So what would be the smallest number in that equivalence class?
Would be 0.5.
Be 0.5, that's right. So I could write this out, I used x over here, as like the set of all y in R, such that, yes, we're gonna need this number to be bigger than or equal to 0.5, since 0.5 would round up to 1, and it's gonna have to be less than what? What would be, I guess,
1.5.
1.5.
yeah, and we're gonna exclude the 1.5 because that gets rounded up to 2. So we have an inclusive inequality on one side and we have an exclusive on the other side. And so if you're having a hard time kind of taking this more qualitative description of the classes and expressing them symbolically, more mathematically over here, I think one thing that might help, first of all, is to just go through some examples, first of all, and think about, just be sure you're comfortable with how the relation is defined. And then just like pick an example, pick out like one equivalence class and list out the elements in that class, describe the elements in that class, and then start to see if you pick up on a pattern. But so for us, these equivalence classes are going to look like for any real number A, then it's going to be the set of all real numbers where, right, we start half a unit below, we include that, and we go up to, but not including a unit above. Where each of these things is representing an integer. I realize that A was used up top. So I don't want to use the same letter. I'll just use a Z. So for each integer Z, we get a different equivalence class. So that's how we can describe each individual equivalence class. And then if we want to describe, well, altogether, what would all of those equivalence classes look like? Our partition would be the set of all equivalence classes Z. Since that's how we get a partition from the equivalence classes, we just say each equivalence class is going to be a different part. And so this means this is just no different than the set of integers themselves. So basically what we're doing is we're taking any real number and we're matching it to an integer, and exactly one integer, and no more, no less. That's why we get a nice partition. We could have picked a different representative for this group, such as that, and that's okay too. It's just not as nice to write out necessarily. Okay, so I'll stop here. I'll put up a solution for the last one. That's, if you want some additional practice, give that one a shot. But I just want to take some time to talk about the exam, give you a chance to ask any questions that you might have. But any last questions on this before we change gears to the exam? Oops. Let's, yeah, so here's what it is. So I just put together a kind of similar looking sheet, but I added some additional stuff at the end. So our exam's on Monday, 2 to 3:15, same general format as the first one. There'll be a part, like a part 1, which is multiple choice, and then there'll be a part 2, which is prove some things. And it will be pretty much very similar in length as the first exam. So as far as that goes, you're allowed to use the same stuff as on the first exam, meaning your own notes. You're not allowed to use anything else that somebody else has created. You're not allowed to use the internet or other things like that during the exam. So before we get into the content and what you might do to help get ready for the exam, any questions about how this is how you guys are gonna take it? It'll be on Zoom again, with your cameras on, and I'll just say, like, you don't need to look at everybody just because your camera is turned on. You could just minimize it. So you don't need to see other people, but I just need to make sure that you're all there. Okay. So, you know, this is kind of the same gist, the same general comments that I had on the previous one. So this is going to cover worksheets 12 through 19. So we have like induction, more induction, even more induction, and then we changed into equivalence relations. And kind of in order to describe a relation, we just needed to make sure that we defined what a Cartesian product is. So that was how we moved through the material. And I'll just say that when you're practicing and preparing for this exam, it's not one of the subjects where like you can just practice a bunch of problems and that's going to get you ready, because you know the problems that we've done, you're not going to see those same exact things again. So I think it's a little bit more important to just take a step back and see like the meta picture of things. Like, okay, when I'm doing proof by induction, how can I get started on that? What are some steps that I can do to do that, rather than just focus on like doing 3 induction problems and then thinking you're good with induction. So I do think you definitely want to practice some problems, but you want to come away from those problems not with, I certainly memorized how to do this problem, but I've got some strategies that I can use to apply it to some other similar looking problems. So I would suggest trying to get the bigger concepts first and then practice some problems. And that's how you can kind of check whether you've got those concepts down, rather than do the problems to learn the concepts. I don't know if that makes sense. So I don't want to make, you know, a sheet for you, because that's part of the process of taking the exam. So in some sense, I think part of the homework that you have is to put together a review guide that is going to work for you. And so just some suggestions on what that structure might look like. This exam is on chapters 10 and 11. So 11 was equivalence relations. So these were the main definitions that we used. So we kind of built from describing what is a relation, what are some properties of a relation. Okay, an equivalence relation needs to satisfy all 3 of those properties. And then from that, we get an equivalence class, and kind of related to this are partitions. So you definitely want to know the definitions, and you want to have them someplace handy when you're taking the exam. There's no plagiarizing when you're doing definitions, right? Because they're very technical things. So you don't have to worry about saying like, oop, I can't use the same exact language that the textbook uses. You know, the definitions, they are what they are. And so you don't need to get creative when you're stating the definitions. And so in addition to that is then, okay, how can we use these definitions in proofs? And so some of the proof techniques that we've gone through are, you know, how can we prove something is reflexive, symmetric, transitive? And if you've got the definitions handy, you know, from the definitions, that should indicate what you need to do. And how do we prove something is an equivalence relation? How can we prove something is a partition? And we've been working with this mod stuff that would be good to be familiar with. And again, if you write out the definition of a partition, that's going to help you figure out how you prove something is a partition. And then kind of the other big portion of this was proof by induction. And so that is a very, regimented process, which is great to have that structure to fall back on. But if you're having trouble, what you're ultimately trying to do is prove some statement that depends on some integer k. So it might help to just write out what that statement is, because that's going to help you figure out what do you need to prove in the base case, what can you assume as your induction hypothesis, and what is it that you want to prove. So kind of identifying what the statement S is, S of k is probably the most important step to get you going. So yeah, then you've got the base case, and something to think about is, how do we, whether we need to check that we've got more than one base case. So we did some examples where that happened. And you want to just take a step back and try and think about the general picture. So like, how do you state the induction hypothesis in general? And the more general your understanding is, the easier it will be to apply it to different contexts. And so when you're working with induction, again, the more flexible you are with the proofs, the better it will be. So for example, sometimes it was convenient to say, we want to prove that S of k implies S of k plus 1. And then there were other cases where we did something like that. And at the end of the day, these are identical. And it's important to convince yourself that that's the case. And then over here are just some suggestions that I gave to myself. That's like, okay, if I get stuck on an induction problem, what are some things that I can do to try and get unstuck? And again, this is a subjective thing. You might have different suggestions that have helped yourself. I'm just suggesting that you try and come up with these sorts of statements. So, okay, I don't know what to do with induction. Let me prove S1, let me prove S2, let me prove S3. And then let me see if I start to pick up on a pattern about how the previous one implies the next one, or do I need the two previous ones to imply the next one, and so on. So it's always helpful to just write out some concrete cases and then try and pick up on a pattern for that. And some other techniques that we've tried is, if you look ahead to what it is that you want to show and you kind of get to the end, then sometimes you can kind of work from the bottom back up. So it's good to know, keep in mind where you're trying to head in the long run. And then, in addition to that, I don't think it's a bad idea to go back and look at the first exam if you haven't done so, since, I'm not going to ask you about injectivity. That was more of a focus on the first exam, but you should be familiar with proof techniques. You're going to have to use those proof techniques. We still are working with sets because that's really what equivalence relations are. So knowing how to prove two sets are equal or subsets of each other, that's useful. And it can't hurt to take a look at power sets, since I think that's still something that people are getting comfortable with. So I just kind of put this together, not as saying like, this is what you should use during the exam, but like, these are the types of things that if I were a student, I would be thinking of when I'm trying to organize my thoughts like this. Okay, so what kind of questions can I help you guys with as far as the exam goes? Awesome. That means everyone is going to get an A. No one has
Sorry.
questions.
I have a question. It's more just about like the setup of it though,
Yeah.
because I know for the first one, Like I tried like finishing it a couple minutes early so I'd have time to scan it, but then I know like at the end you were like, all right, now take a couple minutes to like scan it and like submit it. Is that how it's gonna be? Like, can I actually use the full time and then worry about uploading it?
Yeah, I mean, we'll all be on Zoom. If you are running behind or having some technology issues, or like I'm in the midst of uploading it, it'll take another couple minutes, then just let me know. Yeah, you can just chat me there on Zoom. I'm not gonna like fail anybody if they get me the exam at 3:17. I just don't want people to like disappear at 3:15 and then reappear at 3:45 and say, here's my exam.
Gotcha.
Yeah.
Okay.
Well, if you do have questions, I've got office hours tomorrow, 10:30 to 11:30. And otherwise, there's a study room. You guys are welcome to use that. Yeah, I mean, if you have any questions over the weekend, just shoot me an email. And yeah, just good luck getting ready for the exam. And I did put up solutions to all of the homeworks up to, but not including the one that is due on Friday. So your homework on Friday won't get graded before the exam, but I'll put up the solutions to it so you can at least check your work for that. But you'll probably get your grade on that after the exam.
You can just throw up those solutions like sometime tonight or tomorrow night. Or...
I could, but I won't.
I have a question.
Yeah.
So we're doing the multiple choice part at the beginning, like last time as well.
Mm-hmm.
And so do we have about the same amount of questions as the last exam?
Mm-hmm.
Okay.
Yes.
That should be fun.
I noticed that in like our pre-quiz classes, they lock so we can't view the answers. Is there any way like you can open them so we can review them for the midterm?
I did not know that. Let's see what happens. So I'm gonna pretend I'm a student. And I go to my quizzes. I haven't done any of them, so please don't judge me. So I want to see how I
only
did on
showing
this.
your iPad.
What's that? Oh, I'm still
Still-
looking at my iPad. Thanks.
Yeah.
Yes. Okay, so here is the quiz. So when you click on this, we can't see it. But what happens if instead I go to my grades, and again, please don't judge me. I have all of my assignments are missing and late. And I click on one of these. Can I see my grade? Yeah, I think you could. I just didn't do anything, so that's why I don't see it. But I think if you go, and you all are probably good at Canvas by now, but if instead of going into the quizzes, if you go into the grades and you click on it and you get one of these, I actually did do this one. I got a 2 out of 9, not very good. But if you click on this, I think I just set up this one poorly. But has anyone tried going back? Are you able to see the quizzes?
Yeah, I'm checking right now, and it works how you say. You have to go through the grade. And it just
Yeah.
quizzes.
Yeah, so I guess if you haven't taken the quiz, that seems weird. You're not able to see it. Sorry, that's not my decision. That's like a Canvas thing. But as long as you've taken the quiz, then you should be able to see what you answered and what the correct answer should have been if you got it wrong. That is good to know. Thanks for finding that out. Yeah. So I think it should look like something like this when you're reviewing it. Maybe slightly different since this is the teacher version of it, but yeah. Okay, anything else? Okay, well, good luck, everybody. I am rooting for all of you. I don't, I want all of you to do well. So if there's anything I can do to help you over the weekend, just let me know.
Thank you.
Yep, see you later.
Thank you.
Thank you.